Hello everyone, today we will present our work, HiKER-SGG, Hierarchical Knowledge Enhanced Robust Scene Graph Generation. In this work, we focus on the task of scene graph generation, which aims to extract structural semantic information from visual inputs. We recognize that most existing studies assume access to clean images. This contrasts with real-world situations where images often have corruptions like sun glare, dust, etc. Handling such corruptions is a challenging task as it is unlikely that models can be sufficiently trained to handle such domain shifts. To this end, in this work, we introduce a challenging benchmark corrupted visual genome providing 20 procedurally generated image corruptions, including simple transformations and severe weather conditions. VGC Benchmark offers a comprehensive evaluation platform to assess the robustness of SGG models in adverse conditions. We also propose a novel method HiKER-SGG which utilizes a hierarchical approach that reasons over multiple levels of domain knowledge with increasing granularity in order to generate accurate scene graphs in adverse conditions. In general, HiKER-SGG determines the type of the object by first identifying its high-level type, e.g. animal, before proceeding to more granular predictions by selecting cat among the possible animals. Now we specifically introduce some highlights of our proposed HiKER-SGG framework. Firstly, we construct hierarchical knowledge graphs from external knowledge bases, such as WordNet and ConceptNet, which encodes the common-sense knowledge and hierarchical relationships between object and relation classes. Specifically, the hierarchical knowledge graph comprises a set of common-sense object and relation nodes, and also superclass nodes. Based on the hierarchical knowledge graph, we employ a hierarchical inference strategy, which leverages multi-level domain knowledge to produce precise scene graphs. It classifies objects/relations by initially determining their superclasses, subsequently narrowing the search space to the respective subclasses. Finally, we also integrate an adaptive refinement mechanism to mitigate biases in predicate classes. Unlike previous approaches which typically use a fixed transition matrix, our adaptive refinement dynamically updates the transition probabilities that can convert a general prediction into a more specific prediction during training. It is also important to note that our HiKER-SGG is corruption agnostic. Our model is solely trained on clean images and directly tested on corrupted ones. To evaluate the effectiveness of our HiKER-SGG, we compare the performance of our method with other SOTA method on both clean VG dataset and our proposed VGC dataset. In this table, we report our performance results for the predicate classification task and scene graph classification tasks on clean images in the visual genome dataset. With the hierarchical predicate prediction paradigm, our method consistently outperforms the knowledge other state-of-the-art SGG methods and achieves competitive performance in terms of mean recall. We also show our results on the VGC dataset to demonstrate our method also generalizes well to unseen real-world corruptions. In this table, we illustrate that our method achieves an average improvement of around 4% across all 6 metrics for all 20 types of corruption. Moreover, relative to the clean image benchmark, our method exhibits a lower percentage of performance degradation, showcasing our model's resilience in handling such corrupted scenarios. To provide further insights into the effectiveness of our method, we visualize some scene graphs generated by our method and the baseline GBNet method, under both clean and corrupted scenarios. As we can see from the figure, our proposed HiKER-SGG consistently generate a more precise scene graphs in both scenarios. In summary, our contribution can be summarized as follows. First, we propose HiKER-SGG, a novel method for generating scene graphs via hierarchical inference over structured domain knowledge, allowing it to gradually specify increasingly granular classifications through iterative subselection. Second, we introduce a new synthetic VGC benchmark for SGG, containing 20 challenging image corruptions, including simple transformations and severe weather conditions. Finally, our extensive experiments demonstrate that HiKER-SGG outperforms current state-of-the-art methods on SGG tasks, while simultaneously providing a strong zero-shot baseline for generating scene graphs from corrupted images. Thank you for watching.